This video introduces the last of the basic rules for proofs in SL. Recall that there are 11 basic rules of proof. We've got a reiteration rule, and then we have an introduction and an elimination rule for each connective. The two we haven't covered so far are the two rules for negation, and we'll cover those in this video. Suppose we have this problem. We want to show that given K arrow L and not L, we can prove not K. We could reason in this way. We know K arrow L and not L. But now suppose K were true. It would follow from that, along with the conditional, that L and not L is also true. But L and not L is a contradiction, so that can't be. Our supposition K must be false. Therefore, not K. This pattern of reasoning is such a classic that it's typically known by its Latin name, reductio ad absurdum, or reductio for short. That translates in English as reduction to absurdity. A reductio is a disproof of a sentence by showing that assuming it would entail a contradiction. Reductio is also commonly called indirect proof. Instead of proving something directly, we show that its negation is impossible. Our negation introduction rule will work by reductio. For example, to prove not K, we assume K in a subproof and derive an explicit contradiction. If we spell out the steps in the paragraph we wrote earlier, it would look like this. We write 1, K arrow L and not L as a premise, and then we start a subproof in which we assume K. So this is the supposition, let's suppose K. Then it follows from line 2 and line 1 by arrow elimination, L and not L. That's a contradiction, so we close the subproof and conclude not K. The only problem is, how do we know that line 3 is a contradiction? It's obviously a contradiction. You can see that. If you had to say more, you could provide a truth table. Remember, though, that truth tables are part of the semantics. The proof system is just a matter of applying rules. Given certain patterns of symbols, the rules give you permission to write down other symbols. So the question is, why is the pattern of symbols on line 3 a contradiction? So the crucial thing is that our negation introduction rule requires an explicit contradiction. An explicit contradiction is 2 lines of a proof, where there's some sentence on the first line and the negation of that very same sentence on the next line. For example, we can get an explicit contradiction out of L and not L by getting out L and getting out not L. That would count as an explicit contradiction. Notice lines 4 and 5 meet this kind of proof theoretic, just reading the symbols definition for an explicit contradiction. It's easy enough to get, too. On line 4, we can use and elimination on line 3 to get L. And on line 5, we use and elimination again to get not L. And since we have an explicit contradiction on line 4 and 5, we can now break out, it'll be line 6 now, not K, negation introduction, on that subproof, 2 through 5. This is how the rule looks on the reference sheet. To apply negation introduction, you need to have started a subproof in which you assumed the opposite of what you wanted to show and derived an explicit contradiction. The rule has lines n-1 and n because the explicit contradiction can't just be on any 2 lines. It needs to be on the last 2 lines of the subproof. Notice, though, that the explicit contradiction could be anything. It could be some sentence B and a not B, but B doesn't necessarily have to look anything like the sentence A, which we started with as our assumption. What we want as the explicit contradiction in a reductio subproof is whatever explicit contradiction we can find. Consider this example. Show that given M, we can prove not M. We set up the proof in the usual way. M is a premise. We want to prove not M, and not M is a negation. So we think maybe we can use negation introduction. We look at the negation introduction rule, and we notice it requires a subproof. Here's how the subproof sets up. We assume not M for reductio. We want to find an explicit contradiction. The easiest contradiction to get will be M followed by not M. And in fact, we already have that on lines 1 and 2. But they need to appear one after the other at the end of the subproof. Here we make use of the reiteration rule. It allows us to repeat a line that occurred earlier in the proof. First, we reiterate M, then we reiterate not M. The final step is to fill in line numbers for negation introduction. We're applying it to the subproof on lines 2 through 4. So we write it not I 2-4. Now consider this similar problem. Given not M, prove M. Notice that we can't use negation introduction because there's not a negation in M, which is the conclusion we want to end with. Our negation elimination rule will also work by reductio. So to prove K, we assume not K in a subproof and derive an explicit contradiction. This is how the rule looks on the reference sheet. Start a subproof by assuming the negation of the thing you want to prove, show that an explicit contradiction results, then close the subproof and write down the sentence without the negation. If we look at the two rules next to each other, negation introduction and negation elimination, we see that the only difference is whether you add a negation to the disproven assumption or you take a negation away. Returning to our example, we can plan to use negation elimination by starting a subproof in which we assume not M. The rest of the proof follows a similar strategy. On line 3 and 4, we can get an explicit contradiction using reiteration. Although notice here our explicit contradiction is between the sentence not M and the sentence not M. In any case, we still end the subproof because we have some sentence followed by the negation of that same sentence. So back out in the main proof on line 5, here we use negation elimination on lines 2 through 4. We now have all of the basic rules for proofs in SL. Using only the basic rules, it's possible to give a proof for every valid argument of SL. This is perhaps surprising. Validity is a property of arguments defined in semantic terms. An argument is valid if it's impossible for the premises to be true and the conclusion false. Provability is a matter of manipulating symbols and following rules. Surprising or not, though, it means that proofs are a powerful tool for demonstrating validity. Because QL has all the connectives that SL has, it will also have all 11 basic rules from SL. All we need to complete the proof system for QL is to give an elimination and an introduction rule for each of the quantifiers. That's getting ahead of ourselves, though. Thinking about proofs generally, it's important to keep in mind that you should start a subproof when you're planning on applying a rule that requires a subproof, but only then. Remember, we have 4 rules that require subproofs: conditional introduction, biconditional introduction, negation introduction, and negation elimination. When you have one of those rules in mind, start a subproof. But when you don't start a subproof.